That's what the glaciers do on a much larger scale. Leaves behind it drapes their terrain all around northern New Jersey, but also as the glaciers move, glaciers are moving masses of ice. They bulldoze forward like a plow and leave kind of piles. So toward Denville, there's lumpy hills, ridges. This is what the bright green is. It goes all the way from Delaware River toward Morris County, toward Perth Amboy, out Long Island, up to Martha's Vineyard. That was the pushed edge of the giant ice sheet. We're sitting just north of it. One of the margins of it was right at Denville. So that's in the bright green. The red splotches are where bedrock shows up, where we're going to end up at the Hog Pen. That's hard, that's ancient rock. So we've got really polar opposites of geologic time. The glacial age is recent, geologically speaking, or even more recent, like you know, a few thousand years. So we're going to see rocks that are among the oldest on the East Coast, some of the oldest in New Jersey, 1.2 billion years old, from an ancient mound building event. I'll talk more about that later. That's indicated on the geology map, and they just show as red as bedrock of any sort on the surface geology map. So that's an overview of kind of, so on the way, I'm gonna make you do some work of observation that a field geologist might look at. It's not just boring flatland. You're looking at the trees and the birds, and I'm looking at the ground. I'm seeing rocks and soil that tells this great geological story. So I'm going to try to introduce you to some of that, give you some techniques to figure things out as we go. So you can interrupt me with questions anytime. I'll bring the map along. We can look at it as we make stops.
Do you know how thick the ice sheet was here?
So yeah, it's a great question. We know that it overtops these ridges. So it's at least several hundred feet, and it may have been several hundred feet above that. Maybe, you know, some distance north of it, maybe towards Suffern or a place like that. It could have been a mile thick. It's kind of a steep, abrupt end. So picture like Greenland or Antarctica is, and so yeah, say north of us in New York, it was well over a mile high. Huge amount.
And that was called the Wisconsin Glacier?
That's right. So they name it after where they explained it best. The Wisconsin, then that's the most recent of actually many. During the last 2 million years, there could have been numerous ice advances and retreats and ice advances and retreats that went maybe as far south as Somerville in New Brunswick. This most recent one, the Wisconsin one, went as far as Denville and Morristown. And there's evidence that the earlier ones, older ones, maybe 1 million years old, that went much farther south toward like Route 78, Somerville, places like that. But what we're here is the most recent one.
And is that why it's so rocky around here?
Definitely, yeah. It's the source of a lot of our rocks. And as we walk around, we'll see a lot of different types of rocks. Some are local. Some very well could have come from like the Adirondacks or, you know, elsewhere. So it's just piling it all up here, and we got a good sample of it.
Are we surrounded by...
Started by what? Yes, yes. So Denville sits on the lumpy trees, like that Indian Lake area, you know, mountain lakes. It's all pockmarked with lumpy little ponds. That's end moraine. That's the lumpy end of the glacier right there.
And Long Island.
And Long Island is a classic example as well. Yep.
And is the ice is directly responsible for the Prairie Valley aquifer?
That's right. So that's a good point. They have a lot of our drinking water is coming from those sediments, gravelly, clay, sand sediments. It's more surface. There's two different kinds of aquifers. There's the bedrock, cracked rock aquifers. Those are deeper, probably better water because they're less polluted. And then the more surface that had been like historically for hundreds of years, great sources of water. Yep.
Greg, I got my nerdy question.
Yeah.
We're right on, very close to the border of the Piedmont, right? That's a different soil type because that's not where the Wisconsin Glacier was primarily.
That's right. So we're in this
Highlands.
we're in the Highlands, which is kind of an extension of the type of geology you see in New England or the Adirondacks. And just south and east of us, you get to the Piedmont.
Sandy soil there.
Sandy soils, right. And that would extend all the way down down the Atlantic coast of like Florida. So we're in this province, this rocky ancient province, extends about as far to like Reading, Pennsylvania, and then continues kind of as the spine of the Appalachian Mountains, Blue Ridge, all the way down to like Atlanta, Georgia, as the core of an ancient mountain range. The Appalachians themselves are about 3 generations of piled up mountain ranges separated by hundreds of millions of years. All right, so as I'm walking along in the woods, the prosaic rocks and soil that I see tell a story. One thing geomorphologists look at is not just the rock type of where it comes. I can identify rock types and guess where these come from, things like that. But I also look at the shape and size of the boulders and cobbles and gravel, because that tells a story. The general rule, as a river transports sediment downstream, the sediments get smaller. Why? Because the power of a stream declines as it gets at a shallower angle. This is a relatively steep stream here, so it's pretty trickled out. But if you think of it in a flood, it might be able to move some of those cobbles and boulders. So you think about the finer down there in the valley, there's mud and sand down there. Slow moving stream. Beaver Brook is a slow kind of meandering stream. It's not going to move a lot of stuff. A stream like this, especially if it floods, would move bigger sediments. So you watch for that. Think about the torrents of meltwater coming out of a glacier, like a Niagara River here. What kind of boulders would those be? So watch for that. Metamorphic rock called gneiss. G-N-E-I-S-S, German word. We see chunks of it. The metamorphic rock gneiss, you identify it. It looks crystalline, kind of like granite, but it's got these very recognizable stripes in it of different minerals. Dark minerals, pink minerals, gray minerals. It's got quartz and feldspar and mica like granite would, but it's stripy. Why is it stripy? It's a metamorphic rock. It's been crushed with huge pressures and partially remelted way deep in the crust, miles deep in the crust under huge pressures, and so it's metamorphosed of what it formerly was. It might have been a granite at one time, it might have been a sandstone at one time. It's not completely melted, otherwise it would become magma. It doesn't quite get there, it's just reworked. And sometimes they're swirly and wavy, that's indicating the pressure. So anyways, it's a pretty resistant hard rock. The whole terrain, the whole landscape has parallel ridges of this. A lot of New Jersey's like this. We kind of trend northeast to southwest. And that's the direction of the continents colliding with each other. How old is this? 1.2 billion years old. So that's like 5-6 times as old as the dinosaurs we had in New Jersey. So that time, okay, you've heard of the supercontinents that got together. So the most recent one was the Pangea that made the Appalachians. Well, this is a supercontinent older than that. So Pangea, before that there was like separate continents. Before that there was this previous continent glommed together called Rodinia. 1.2 billion years old. You wouldn't recognize it. There was no life, no terrestrial life. There was microbes and things like that in the oceans maybe. There might have been some microbes on some.
About leeches.
What's that?
Leeches.
No, not even them. Just really rudimentary stuff, like archaea bacteria and like, single cells. What's that?
Streamophiles?
No, what is that? You've got your Paleo Biology here. What's that one?
Microbes that could survive in some of the.
Oh yes, right. So it's crazy. Yes, crazy. It's an environment that probably had not enough oxygen on the planet, acid atmosphere. It could have been there's a period in there we were an ice planet, like Titan or something like that. The whole planet was covered with glaciers. There's also times where it's just rocky steam planet. Depends on what age it is. So it would be totally unrecognizable. More Mars-like or Venus-like. So not much fossil record of it, they're guessing. They find out the age of the rocks by radiometric means within the crystals. You know, radioactive decay in the crystals is how they get at it. So that's the kind of rock that's very common in Morris County, in the Highlands area of New Jersey. East of us, that's the Newark Basin, much more recent rock, that's dinosaur era, Mesozoic rocks, there to the Hudson River, to the coastal plain. And then west of us, the Appalachian Ridges, Kittatinny, Sunrise Mountain High Point, those are Paleozoic sedimentary rocks, like similar ones in the Appalachians. Those are 300, 400 million years old, but you know, quite a bit younger still than what we're walking on, the core. And ignoring the fact that we've got glacial sediments only 20,000 years old draping everything here. So,
hey, Greg, educate me on this. If I put a blindfold on you, spun you around New Jersey, put you here, tell me why I'm in the Highlands based on the geology.
I would look around at the terrain. I'd look for parallel ridges. I'd look at the rock types around here and I'd say, oh, nice, metamorphic rocks, something, you know, it's a different environment here.
Nice spelled with a G.
G-N-E-I-S-S, nice.
Yeah,
That's right. The main, yeah, is, you know, a lot of geology names are German. I don't know why. Nice, schist, S-C-H-I-S-T is another metamorphic rock. It's finer grain, looking flaky, but it's crystalline. And then we have things like quartzite and marble. Marble is a metamorphic rock. It used to be limestone. There's decent outcrops of marble up and down the highlands here in New Jersey. Franklin mines are built into that kind of stuff too. That's metamorphic, formerly sea sediments, ocean sediments. So we've worked our way up this ridge. It's kind of elongated ridge. We're taking this detour here. We're on top of this rock outcrop, and the terrain on either side of you changes dramatically. It's shockingly weird. It's we've had this, you know, kind of the ridge. We walked up it, we felt it, but it wasn't like dangerous or anything. And the rest of the rolling terrain. And here we've got, behind me is a 100-foot cliff, and there's another one over there. We're in this little peninsula, the Hog Pen. Why the heck is this here? All right, so Mike brought me up here. I'd never been up to see it. It was kind of jaw-dropping for me, geomorphology, this dramatic terrain. You know, I would thought, well, is this a quarry or something excavated? No, this is natural. So I have a couple theories as to why these enclaves, these ravines exist, both having to do with glacial erosion. All right, it could be wall of massive continental glacier coming over us here, and like I was saying, up on the top of the ridge there, gets a downhill side. It begins to, it had been melting at its base. Now it's refreezing. It's beginning to pluck out, and it's just, you may have seen this in mountain areas, and they sometimes happen in continental glaciers coming off this ridge. This might have been literally an ice fall. It cracks and crevasses and works its way down here to lower terrain into this valley as ice was coming over here. A second theory is that it's maybe a meltwater plunge pool. On the geomorphology map that I showed earlier, we could pull that out in a little bit. They map some arrow streamlines of what they think meltwater went down, and one suggests that there was meltwater coming down here. So subglacial river that might have been pouring out of here, excavating in a really vigorous sense, like Niagara. You know, this terrain, this relief here is not much different than if you've been to Niagara Falls. It's a little smaller, but the depth is similar. So it could have been actually meltwater that have excavated out these two ravines, the Hog Pens. If it was that case, I would look for downstream, down toward, is it Cedar Lake down there?
Yeah, Cedar
Right. Boulders that had been washed down there. So you think about it. Now, if we get a chance, if we're going to go see, if the weather holds, we could see the ginormous erratic. Picture the, when I first gave you the idea about the water moving sediments, gravel, pebbles, sand, boulders, the power of water to do that. Picture the power of water, the size of a Niagara River torrenting down. That could move some pretty big boulders, but nothing comparable to what the glacier itself moves. So all these little boulders we've seen have been dropped by glacier erosion. Glacier has no problem moving that, but the gigantic erratic boulders, they're called erratics because they're moved from someplace else. They're erratically placed and they look different than what should be here. So we'll see those, and they're anything that can move the size of something in the house. And we have a lot of famous ones in New Jersey. Glen Rock, the town of Glen Rock, is named for one. There's a couple at Rockaway Mall. They've managed to put the parking lot around. They're still around, and they're easier to make landscaping rather than blast apart. They're so big. So we have plenty of those in New Jersey, and we're going to hopefully see a big one. So the idea is that nothing but a massive glacier could move something that big. So, and the massive glacier is also doing massive erosion and taking out chunks of rock. Oh, yeah, okay, so we have one right close here. It's the same kind of rock. Okay, now I'm sitting on a glacially eroded one. It's smooth, bouncing any scratches in it. But that boulder perched there behind the oak tree, we're going to see it from below. It's a balanced rock. We have some balanced rocks in Wildcat Ridge, places like that. That's an erratic. What shape is it according to your cards? You tell me. That shape of that boulder perched there. What would you? Is it rounded, sub-rounded, angular, or subangular? What do you think? I hear subangular. What are the other opinions? You think sub-rounded? Some say subangular. All right, so it's not totally angular. It's moved some. It's not totally round. It hasn't moved very far. It's the same kind of rock as surrounding here, so that makes sense. But it was dropped there just in time before it fell off the rest of the cliff. And it's been there 18,000 years until something erodes it further. So, but that's the example of the shape of the rock telling me the story. How did it get there? All right. Okay, so should we wend our way back down?
One question before you.
Sure.
You were commenting on the difference on one side of this ridge to the other.
Yeah.
So what's the big difference?
So up here we've kind of reached this kind of smooth slope, and behind me is a precipitous drop of 100 feet. So if you want to take a look, be very careful, right?
How about this steep slope right
Same thing.
running water also for
Yeah, I think it's the glacier erosion, yeah. So there's two kind of alcoves here that were of the same formation. They could either torrential water erosion or the glacier plucking, either way.
What
the
time
big
are we?
piece of ice sitting right in the back of you melting.
Picture ice hundreds of feet above me and falling over this, eroding it. All right, anyway, you get a sense of the two, we're in this precipitous valleys here. You could picture if there's these big old angular chunks of rock have just, fallen out of the wall there. Over there we saw that too. So I could picture, glacial ice latching onto that. I'm trying to figure if it's, we also, see if you can confirm this. Geomorphologists, field-wise, we also look at topography, shape. The shape of this valley, you tell me, is it V-shaped or is it U-shaped? If we're looking up valley, what do you think? You think V? V.
I say you.
Some say U. V. We could vote. Let's vote on science.
Well, peer review, yeah.
Right, peer review. I approve this one. Okay, so if it's V, that would be of river kind of erosion. If it's U-shaped, it would be glacial erosion. And it could be, I guess, a blend of it too. But that's something we could have a surveying crew. We could walk down the hill and up there with a tape measure and things like that. And we could plot it. Some of our bigger valleys, like maybe Beaver Brook Valley, those are U-shaped because that's a channel for glaciers to go down. So what is this alcove? We could investigate that further. I think we should bring geology students here for a field project and sort this out. That's a good granite texture on there, but it's not granite because it's striped. It's got stripes in it. So the original rock was granite. So that means older than 1.2 billion years ago, there was a granite. Who knows how old that is? And that's the granite texture. It's got quartz and feldspar, and the black is hornblende, so it'd be a hornblende granite. But then it was metamorphosed and made stripy and folded. And if you look at my map, the geology map is also swirly and folded on a scale of many kilometers. Same forces. The forces that's bending this rock around is bending the whole continent, basically. It shows up. And so you can see it. So the vein of quartz and a line of the biotite and the hornblende, you can see on that rock there, pulled up. So yeah, if you get as you file out and head your way back up, you can if you got any questions about the map, and then I'll follow on. Are we?
Here's some pudding.
Oh wow!
Dessert.
There you go. What's that? Okay, so all right, I'll do the pudding stone next. Did you take that out of the fireplace? So this is here's. So on your video, that's the texture. The dark minerals are hornblende and biotite mica, and the pale minerals are quartz and feldspar. That's typical granite. And then on this side, you can see the stripes, quartz, hornblende, something lighter like that in stripes. And then this is broken up, but that's the pudding stone. This is the Green Pond Conglomerate. It's got a purplish maroon matrix of sandstone, all cemented by quartz itself with pebbles of quartz. So it's really hard.
So that's metamorphic also?
This is not quite metamorphic.
Sedimentary?
It's still sedimentary. It's very, very old though. It's 400 million years old. It's well compacted. There'd be very little pore space in here. But, and you know, you can see the pebbles. The pebbles look a little elongated. That might be a little bit of metamorphism, or it could be that there's like, you know, oval shaped pebbles that kind of align themselves. There's layers in here. This is a gravel stream sediment coming off an ancient mountain range. It's, you know, coarse conglomerate like that, so that means it's nearby the mountain range as opposed to farther out in the plains. This would be kind of an alluvial fan, kind of just shedding off near the mountain front of an ancient mountain range about 400 million years ago. That's the good example of the Green Pond Conglomerate. And this is this would have been buried under, you know, miles of sediment. So it's exposed now, but if it's 400 million years, this is Silurian. There would have been, you know, Ordovician and Pennsylvanian, and then all the Mesozoic, and then all the Cenozoic. Just many intervals of sediments above it that would have really compacted it. And then there's, you know, heat and some pressure. Even, you know, it's not metamorphic, but still enough that's compressed it and lithified it. So the
ridge that comes out from a ridge in Green Pond, that's an alluvial fan?
yeah, it used to be an alluvial fan. It used to be that steep ridge, that steep mountain ridge, was a kind of a moderately tilted alluvial fan 400 million years ago. Then buried, and then tilted tilted, you know, the sedimentary rock that used to be flat lying is now like that at Green Pond.
So the rest of the mountains just eroded away?
Eroded away. They would have covered the entire region, and that's the last remnant of it. So we have faults in New Jersey at this compression area that go up like this. Like San Andreas fault, that goes like this. Faults in the Newark area, they go like that. Faults here in western New Jersey go like this. They overthrust each other. That's a violent compression at the continental scale.
What are the different colors on here?
So this is the surface geology. If it's red, it's the bedrock, undifferentiated. It could be any kind. If it's the orange, this is a lake bed. The blue is modern swamps, or maybe a few thousand years old. The green is the drape of glacial debris as the glacier melted back. Could be a foot or two, could be hundreds of feet. And this lime green is the same stuff, but this is the end moraine of it. This is the end margin of that glacier. The same stuff piled up in lumpy terrain. There's lakes. This is Denville Mountain Lakes. That's the margin. It would have gone all the way around. Here's the map of inset. Here, this one. This is northern New Jersey. That green margin is the end of the glacier, of this part here.
And we're like right about here.
And we are right about here, I think.
Okay.
Yep. There's that arrow I was talking about that makes the.
And the purple is.
And that purple is. It's a kind of a outwash. It's glacial debris that was washed out and flooded, making a terrace.
Okay.
Kind of a floodplain like.
Is Denbrook on that map?
Sorry?
Denbrook, the brook that's called
Den Brook.